Today we're going to talk about polyprotic pH curves. Polyprotic meaning many, of course. Some pH curves have two distinct changes, drastic changes in pH. So they'll have two sharp rises or two sharp drops. Therefore, there is two quantitative proton transfer reactions taking place. I gave you guys notes. All right. Therefore, there's two different quantitative proton transfers. In other words, there's two times where this H plus is completely changed into something new. It's completely donated to change into new substances here as we go through this. So, for example, the first one here, we look at the titration of carbonate with HCl. What happens when you titrate a carbonate with HCl? First of all, should we be starting the pH high or low? You better know. Should be starting high. Look, even the graph tells you guys. You're adding HCl, right? HCl has to be in the burette, yes? So what's in the bottom? It's the base, yes? Also, we know that the titration of this with this, remember, is the burette. Yes? This is, of course, what we call the aliquot. Yeah? Okay? So, we know that we're going to start high here and work our way lower. It has two distinct endpoints here. When you look at this graph, you'll see the following happens. Okay? The first part here kind of actually does a little funny little thing like this. Kind of starts out like that. It dips down, levels out, dips down again. There is two distinctive endpoints with a polyprotic pH curve. There is two what we say quantitative transfers here, and also, okay, two rises, two drops, two sharp ones. Okay, so I don't know, honestly. I tried this last class, and I got to be honest, it didn't really. That's not really a great graph, this one, but that's okay. Okay. What happened in the last one, of course, I kind of ran out of room, so hopefully I'm kind of hoping I don't do that again, but we might. Now, all we're going to do here, guys, is just talk about what's happening at both of these endpoints here. You're going to get two endpoints here. That's all we're going to worry. We're not going to worry about concentrations or initial pH. We don't have any numbers to do that with. We don't have concentrations or volumes here. We'll worry about that later, trust me. Okay? So what happens in the first reaction here? Well, in this first reaction here, we're starting with obviously carbonate, right? Yes? We start with carbonate, and that's the only thing that's in the bottom of that beaker, yes? Okay? When you guys went to the lab, that's what's in the bottom of the beaker. So we're starting with that. We're adding HCl. So really we're adding a what? Are we adding HCl? No, we're adding H3O, right? Hydronium ions, right? So we're adding H3O plus, yes? This is a quantitative process. In other words, what that means basically is this. Eventually, we're going to keep adding it. It's not equilibrium, okay? We're going to add it. Yes, the first part probably is equilibrium. We add a little bit, it equals out. We add a little bit, it equals out. We add a little bit, it equals out. Eventually, what we're going to do is we're going to add so much H3O plus that it's going to completely turn into, okay, it's a quantitative process. It completely turns into proton donor, proton acceptor. So we're going to get some water here and some HCO3 minus. Yes? Okay. That's what's happening from basically here, well, right about here, all the way to there. Yes? That's the reaction that's taking place. That's the first reaction that takes place. We add a little bit, it equals out. 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 We add just the right amount, we get to here, right? And then after that point, we are now going to have products after that point, okay? So basically what I'm saying is this part here, okay, is this reaction here, of course. That's what's taking place in that section, yes? Okay? Yes? Now, I don't know a lot about this, except for, of course, this is now completely reacted to give me this and this. Okay, I know that this is a pH of 7. Can I predict the pH for that, just like I did before? Now I don't know what concentration I started with, right? And that obviously has effect on it. But could I predict that pH? Think back to yesterday. Did we do that yesterday? I mean, we start with some concentrations, obviously, yes. But I could kind of eyeball it, yeah? Could I not? What do I get produced there? I get water and hydrogen carbonate. So what is that? Get your data booklets out. Well, is that an acid or a base? It's a... you sure? It's both. Is it not? What's that called? You better know. Huh? No. Amphiprotic is the correct term for that. Amphiprotic, right? HCO3 minus, if you look on the left-hand side, you'll find it. You'll also find HCO3 minus on the right-hand side. How do I know what it is? How do you determine? What did we do with amphiprotic? We did what? I made you guys do some extra work with those. You had to compare Ka and Kb values, yes? Ka is easy because you just look it up as an acid, right? So Ka value for HCO3 minus is, you just look it up, guys. It is 4.7 times 10 to the negative 4, is that right? As an acid. Is it 4.7 times 10 to the negative 4? Yes? When you find that one on the left-hand side, yes? HCO3 minus. Oh, I did that last class too, sorry. You're right. I can't read my own writing is the problem. That looks like a 4, but it's 11, yes. Okay, so 4.7 times 10 to the negative 11, yes? Look that up on the left-hand side. What is it as a base? Well, remember, to calculate the base one, this is good review here. All this is good review, guys. Conjugate acids, conjugate bases, all that good stuff. You need to take 1 times 10 to the negative 14 divided by HCO3 minus as a base. So you got to look up the conjugate acid of that, yes? Which is, I actually forget that number there, but it is, let me find it here. What's the conjugate acid of HCO3? H2CO3, right? So find HCO3 minus as a base. Okay, there it is right there. The conjugate acid is H2CO3. That's 4.5 times 10 to the negative 7, yes? So I'm going to divide those two. Kb here should work out to be, I think I have that number here, 2.2 times 10 to the negative 8, yes? Okay, good. So, question, is it an acid or a base? Is HCO3 minus an acid or a base? It's a base, yes, because the base is the higher number. The Kb value is higher, so it acts as a base. So this is acting as a weak base. All right? Now, I can guarantee you one thing for sure. And you should be able to guarantee me this as well. This right here is called the endpoint, yes? Yes? That is a pH greater than 7, correct? Has to be, because it's acting as a weak base. If you want to ballpark it and look it up, you can. Okay? There is some factors that affect it, of course, which we didn't really talk a lot about yesterday, but you could ballpark it if you want to, I don't care. But ultimately, I need you to know that that's above 7. Okay? That's the most important part. Good so far? Okay. Now, next, what's happening at this section here? To this section here. Okay? What's happening there? Well, remember, I don't have carbonate anymore because I've completely changed this carbonate. It has basically accepted that proton to give me this now, right? HCO3 minus and water. So at that particular point there, I've now converted all that carbonate and hydronium into HCO3 minus and water. It's a quantitative process. It's completely changed. It's not in equilibrium anymore, okay? This part was probably in equilibrium right here, all the way up to here. At this point, it changes into the products only, okay? Because I've added so much HCO3, or H3O plus, that I now have just the product, okay? So now I have water and HCO3 minus. Well, we always have water. So really, what do I have here? From this point to, let me do a different color here. This point to this point here, I'm worried about HCO3 minus, aqueous, my weak base, yes, reacting with my acid, H3O plus still adding the H3O plus from the burette, right? Haven't changed that, still adding HCl from the burette, still coming down, okay? And that would give me some water. And of course, proton donor, proton transfer, I'd now get some H2CO3 aqueous. All right? And that's what happens in that section there. And once again, basically, yes, equilibrium, 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 sharp change. After that part, you'd only get that part there, the water and the weak acid, H2CO3. Okay? But that's what's happening in that section there. And yes, it's in equilibrium at first, but eventually it's going to completely donate its H+, completely change into those two products there. Now, what's H2CO3? This is a pH of about 7, right? What's H2CO3? Acid or base? Acid, okay? You don't need to look that one up. That's not amphiprotic. That's just an acid, yes? So this is a weak acid, yes? So if I had to take this over to here, right? What's that pH going to be? Well, I can guarantee you it's less than 7, yes? Okay? And once again, if you really wanted to ballpark it, I guess you could, but ultimately that's what we need you to know. Okay? Is that good? Any questions so far? Yeah. Yeah. See what side that's on. It's on the left side. Okay? So that's kind of what we're going to be doing today. By the way, I probably should mention this to you, and I'll prove this to you later actually, but regardless, doesn't matter. Okay? What color can I use here that I haven't? I've pretty much used every. If I went down here, what's that part? What's this called again here? For that first endpoint, what's that called? Equivalence point, yes? I don't know what it is because I don't have any concentrations. I don't have any particular volumes and stuff. But let's say that turned out to be X there. X. Okay? It turns out, and I can prove this to you later, it doesn't really matter, but it turns out that if that's X, this right here is 2X all the time. Okay? So if it takes 10 milliliters for the first reaction to take place, it's going to take an additional 10 milliliters for the second one to take place, or basically 20. So 10 for the first one, it's going to be 20 for the second equivalence point. If it was 30 for the first one, it's going to be 60 for the second one. Always. Okay? Basically how that works is, for this reaction to take place, it takes, 25. For this reaction to take place, it's 25. So a total of 50. Okay? So that it's always equal proportions, always, 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 always. Okay? So two endpoints can be explained by two different proton transfer reactions here. All right. Proton transfer number 1, which you guys already wrote down. Okay. Proton transfer number 2. All right. So if yours is kind of messy, like I said, I don't really like this because I wish they were a little bit bigger here, but they're not. And I always run out of room here. So if yours is really messy, then there you go. You have some for those two there. H3O plus is a monoprotic acid. H3O plus. So HCl, HNO3, things like that. It can only donate one H plus. Okay, it's only got one H plus, or H3O plus basically. Carbonate is a polyprotic base. It can accept up to 2 hydrogen ions. It can do that because, look, carbonate has a 2- charge. How many H pluses can I put with it to basically neutralize it out? Well, 2. Okay? All right? So it's a polyprotic base. It doesn't matter if it accepts 2 or 3. It doesn't matter. It's polyprotic. It means it can accept more than 1 H plus. All right? Monoprotic acids look like this. They're H3O plus, they're HA. So HCl, HBr, HNO3, HI, I guess. Things like that. Monoprotic bases would be things like sodium hydroxide, potassium hydroxide, hydroxides basically. Okay? Polyprotic acids look like this, H2A or H3A. So examples of that, polyprotic acids, sulfuric acid, H2SO4, phosphoric acid, H3PO4. Okay? They have more than 1 H plus that they can donate. H2SO4 donates 1 H plus, and then you get HSO4 minus. It donates another H plus, and then you have SO4 2 minus. Okay? So that's a polyprotic acid, H2SO4, H3PO4. Polyprotic bases are either B2 minus or B3 minus. Like, for example, oxalate, OOCC002 minus is a polyprotic base. It could accept H plus, and then it could accept another H plus. Okay? Phosphide might be an example, P3 minus. It can accept 1 H plus, could accept another one, and another one after that as well. Okay? So we'll look at that today. All right. This one shows 2 distinct endpoints. I want you guys to go ahead and draw the graph here. It's phosphoric acid and sodium hydroxide shows 2 distinct endpoints. Once again, you'll know that these are polyprotic because 2 things. First of all, in the question, when you see 2 distinct endpoints, you know that it has to be polyprotic curve. 2 rises, 2 drops. Shh. When it says that. Also, look at the acids and the bases that you deal with. This is phosphoric acid. Phosphoric acid is H3PO4. Geez, I could probably donate an H plus, and I could probably donate another one. I might even be able to donate another one after that. You can't, but you might be able to. Okay? So there's a lot of H pluses that I could donate there. That's good right away. I'm thinking if I donated one and then I donate another one, I got to see that 2 double rise, right? And of course, sodium hydroxide, well, that's monoprotic. That's only 1 hydroxide, but that's okay. All right? But I have that acid that can donate more than 1 H plus. So I think 2 distinct endpoints. Okay? Without looking down here, if you just look up here, remember, it's titration of this. This is what? This with that. This is the burette, yes? This is the aliquot. So, right? If you look at the graph, it tells you I'm going to add so much sodium hydroxide. So are we starting low or high with this one? Low, okay? So phosphoric acid is what we're starting with at the bottom here. So it kind of does this little thing here. I'm going to try and start a little bit lower here just to... Okay, kind of does that, up, up, and once again, those are the points we're interested in right there, okay? Those are kind of the points. I kind of exaggerated the first part maybe a little bit, but that's okay. Once again, we could find the initial pH by, of course, taking the phosphoric acid and figuring that out with the Ka value, et cetera, et cetera. Okay. Well, what's happening here? Well, first part here, right? Look, phosphoric acid, strong or weak acid? Phosphoric. It's weak, yes? So it's a weak acid. So once again, that's going to stay together. H3PO4 stays together, yes? Sodium hydroxide, strong base, completely dissociates, so I got hydroxide, yes? I think you guys probably understand that this is my strongest acid here, and hydroxide would be my strongest base. So I'm going to react those 2 together, and that's going to be this part right here. Maybe what I'm going to do is I'm going to write this maybe down here, I think, because I think I'm going to run out of room if I try to do it somewhere else. So phosphoric acid and hydroxide Okay? Quantitative, of course, we're going to do a titration, so it's going to completely change at some point. I'm going to get water and H2PO4 minus. Okay? And of course, the part that I'm talking about would refer to that point right there, yes? Okay? I just don't think I'm going to have enough room, guys, because I just don't. Okay? Is that good? H plus is dominated by the phosphoric acid, so it goes to the water. If I take off an H plus, what do I have left? Well, PO4 is a 3 minus. 3 H pluses. If I take one off, I got 2 H pluses and a 3 minus, so that's H2PO4 minus, yes? If you're not sure, grab a calculator. Okay? That might not help you, I don't know. But that's what you need to have for that. Once again, you say, okay, well, I don't have any concentrations and stuff like that, and we'll get to that eventually, but I don't really have any concentrations or volume or equivalence point. I do know that, though, this here would be called X, maybe, for example. I don't know what that is exactly, but we'll find that out on upcoming questions here. However, what is this pH going to be right here, I guess, is the question. Well, I guess the question is, this is a pH of 7, of course. What is this? Is that an acid or a base? Or is it both? It's technically both, yes? Yeah, it is. Okay? So we need to, once again, always compare. So if that is both, and you better make sure that you look and see if it's both. It's not always going to be both, okay? So just keep that in mind. Usually it is. But, well, for the first one, it almost always is, okay? Or maybe it is always. The second one that we do, yeah, that's debatable. It could or could not be. We'll see, I guess. H2PO4 is an acid. Let's see, that's 6.2 times 10 to the negative 8. Okay. As a base, H2PO4 minus is, well, that divided by 6.9 times 10 to the negative 3, yes? Is the Ka value that would go with that. And let me see, do I have this written down? I should. Yeah. All right. So the Kb value works out to be 1.4 times 10 to the negative 12. Okay? So, which is bigger, Ka or Kb? Ka. So, Ka is larger. So, Ka is larger than Kb. So, therefore, this is acting as a weak acid. All right? And therefore, my pH, therefore, for that endpoint has to be, of course, pH of less than 7. There. Okay? Now, that's the first one. Now, let's move on to the second one. Now, we're going to take this H2PO4 that we've completely converted here. So, my H2PO4 minus and hydroxide gives me proton donor, proton acceptor, HPO4 2 minus, and water. Okay? So, lose an H plus again, or basically proton donor, and water. Same kind of thing, okay? We need to decide, is this a weak acid or a weak base? And that'll kind of tell me where that endpoint's going to be, roughly, approximately. And in that case there, you're going to have to look those up again. Is HPO4 2 minus, is that an acid or a base? It's both again. So in this case, you'll have to do it again. Okay? So find the Ka value for that. Find the Kb value for that. The Ka value works out to be 4.8 times 10 to the negative 13. Is the Ka value that goes with that. The Kb value is, of course, 1 times 10 to the negative 14 divided by 6.2 times 10 to the negative 8. And that would work out to be, does somebody have that? Anyone? No? I can tell you right now, though, it's going to be not as big as or it's going to be bigger than the Ka. The Ka value is pretty darn small, isn't it? Kb is probably going to be bigger than that. What is it? Okay, thank you. So we can see in this case that the Kb value is larger, so now it's acting as a weak base. Therefore, once again, and here, let me take this. That's that point right there, yes? Okay, so I know that that right here, pH has to be greater than 7, yes? Are they always going to be less than 7 and greater than 7? Could they both be bases? Could they both be acids? Anything's possible. So yes, it is possible. Okay? So it doesn't have to, don't assume because this is less than 7 that that one's above 7. Don't assume that. Okay? That's not the case. And in fact, I'll give you an example here coming up. Okay? So it depends. You have to check it out. You have to make sure you do the work for that. All right? So that is greater than 7. Once again, if you wanted to, you could probably try and predict those roughly. I mean, it depends on many factors, but we could probably pick some colors for that. Okay? By the way, if that's X, right there, that's 2X. Okay? So if it took 15 milliliters for the first one, it's going to take an additional 15 milliliters or up to 30 milliliters for that second titration to complete itself. Okay? Good? All right? Well, that's easy, right? Moving on. So there's your two equations again. Like I said, just in case yours are messy or whatever the case might be. There's two proton transfers here, right? There's 2 times proton donor, Bronsted-Lowry acid, Bronsted-Lowry base. Yes? Okay. Proton donor, proton acceptor. All right? Same thing here. Acid base, proton donor, proton acceptor. Right? There is, oh, yeah, I didn't set this up very well. Going back to here, okay, some people are going to say, hey, look, HPO4 minus, does that have an H plus that it can donate? Is there an H plus left in that? Could I do a third reaction? The answer is yeah, there's a third. There's H plus in there, yeah? So it is, it's definitely polyprotic. It's got 3 H pluses it could donate. So do I have to worry about the third equation? And the answer is no, because it says there's 2 distinct endpoints. Okay, so that means there's only 2 sharp rises in the curve, which means basically you're done. Is there another H plus there? Yes, there is. That reaction doesn't take place though. Do you need to know that? Not really, no. Because it's going to tell you that there's only 2 distinct endpoints. You wouldn't have to do this a third time. Okay? But basically that's what they talk about here. A third proton transfer reaction is possible since HPO4 2 minus is a weak acid. There's an H plus right there that it could donate. So this is what that reaction would look like, right? HPO4 hydroxide gives you water. I should have had the double arrow there. And PO4 3 minus. But what you see is double arrows in this case. That is not a quantitative reaction. How do you know that? Because I'm telling you that. Okay? You don't know that it has only 2 distinct endpoints. So if there was 3 distinct endpoints, then that would be a single arrow. You would know that that totally turns into that. But because that acid is so weak, it doesn't have the ability to basically change into those products. It's too weak of an acid. It can't completely react. So in this case, the HPO4 2 minus is just simply not strong enough for this reaction to be quantitative. All right? So therefore, it's just going to sit in equilibrium. You can keep adding hydroxide, but this isn't strong enough to donate its proton to that. Okay? So that's not going to happen. So the most you're ever going to have to worry about is 2. Okay? That's it. You'll never have to do 3, but okay, just so you know that some of these acids do have another H plus there that is possible to donate. Here you go. Here's some numbers with this one. Oh boy, think of the possibilities with this, eh? All right. Let's start with a graph. Starting high or low? Quickly. What do you think?
Low.
Starting low, yeah? 25 milliliters of acid. These are even easier to tell because they tell you it's 25 milliliters of acid. You're not going to put 25 milliliters of acid in the burette. That doesn't make sense. The burette's is there to measure out the volume. So obviously the base is going to go into there. So you're going to start low, right? Let's draw a graph. What does the graph have to look like? Do I have to worry about exact graphs here? The answer is no. Okay, that's not your job. But you do have to understand that this is a polyprotic curve. Okay, it kind of starts out like this. Sharp rise, like so. Okay, and mine's not the best graph, and I don't care. All right, there you go. So 2 distinct endpoints. I think it tells you that right here. 2 distinct endpoints. Okay, let's start with the initial pH. Go ahead and do that right now. What's the initial pH going to be? This is review from yesterday. That's all it is. All right, I'm going to start writing out the equation here, guys, but go ahead and keep working there. Where's my... All right, so to calculate the initial pH, I really wish I could do this on the graph here, but I just don't have enough room, I don't think. We have H2C6H6O6 and water, of course. H3O plus and proton donor, so HC6H06 minus. All right. We're starting with a concentration of 0.5 molar. What is that? C6H6O6? I forget now. And we need to figure out the initial pH, yes? So we're going to do the Ka x squared over 0.5 molar. Ka for that is what? 9.1 times 10 to the negative 5? Should be right. 9.1 times 10 to the negative 5 is x squared over 0.50. X, when you solve for x, of course, I'm going to take a little bit of a shortcut because I'm assuming that you guys can do this by now, is about 0.006 molar, roughly. And you take the negative log of that, okay? And the pH of this one here would be 2.17 to start, yes? Hopefully that's what you got, I hope. Yeah? Because that's the easy part. All right, so I go back to my graph here, and what I've done is I've calculated this right here. That's 2.17, okay? That's exactly yesterday's homework. That's nothing new, okay? So if you did yesterday's homework, that should be a breeze for you there, okay? Good? Now, that's before I add any hydroxide. The hydroxide, of course, is in the burette. So now I'm going to start adding some hydroxide, so I need to make a reaction with that acid and the hydroxide, of course. So, second part, I'm going to take my H2C6H6O6 acid, and I'm going to react it with some hydroxide. And it's yes, initially it's going to be in equilibrium. I'm going to add a little bit of hydroxide, add a little bit, add a little bit, add a little bit. It's going to go back and forth, back and forth. I'm going to add too much. It's going to shoot up, right? Somewhere in between there is where that was a perfect balance, a 1-to-1 here. And I'm going to get water, of course, and HC6H6O6 minus. Okay? Good so far? Yes? That's up to my first, basically, endpoint. That's what's happening at the first endpoint. I have some numbers for this, so I could find out the equivalence point of this, yes? This is yesterday's stuff, homework. That's why I said if you do your homework yesterday, you'll probably be okay today, because this is exactly the same thing here today. We have 25 milliliters of acid, 0.50 molar. We can find N. N works out to be 0.0125 moles. I'm going to move that over to here. That's 0.0125 moles. V and C. And I told you that it was a 0.40 molar solution of sodium hydroxide. Those things come right from the question, except for the N, of course. I got N and I got C. I divide the two of them, and I get 0.03125 liters, or 31.25 milliliters. Okay? Good so far? That's the equivalence point. Yes? Yes? So, let me go back up to my graph here for a seckie. Right here. 31.25 milliliters is what I'm going to put there. What's that pH going to be right there? I guess that's something else we need to talk about. Okay? So, that's yesterday's stuff right there, up to this point. Then I'd say, okay, is this a weak acid, or is this a weak base? Or is it both? And it turns out it is both. Okay? Once again, you need to compare Ka and Kb values, right? So, comparing those two. Let's see here. So, let's do that. What's the Ka value? Does somebody have that handy? Anyone? No? 2.0 times 10 to the negative 12? Is that right? Okay. And then what's the Kb value going to be? Well, once again, we need to look that up. Now, I probably shouldn't have done that there. I kind of, that's okay. I got to do it somewhere, I guess. And then, let's see here. Okay. Kb value. Where are we here? There we go. So, that divided by 9.1 times 10 to the negative 5, yes? And that'll tell me Kb, right? So, let's see, which one's going to be bigger? I imagine Kb is going to be bigger. Is that true? I imagine. Sorry, 1.0 times 10, I'll just double check here and get you a number, divided by 9.1 times 10 to the negative 5. Yeah, 1.1 times 10 to the negative 10. Not by much, but it is. So, Kb is bigger. So this is acting as a base, yes? Okay? So I started at 2.13, remember? Pretty acidic. And already it took 31 milliliters, it shot up to be already being a base, yes? So right here, I would say the pH has to be greater than 7, because it's acting as a base, yes? Guess what? So is the next one, right? The next one has to be a base too, doesn't it? So there's a prime example where both of these endpoints turn out to be on the basic side. Okay? Now, good so far? Yes? That's all review stuff except for the amphiprotic part that I added on in the blue part there. But other than that, it's all the same. Good so far, yes. Now, well, let's try and blow your mind a little bit here. So, let's go on to the second equivalence point. What does that look like? Well, let's take a look here. Once again, I'm going to start with this now because remember, now it's completely this stuff here. I got water and I got that C6H6O6 minus base. So I'm going to start with that. Okay? HC6H6O6 minus aqueous. And I'm going to add more hydroxide to it. I think that's what I'm adding, right? Yeah. More hydroxide to it. And this is still got an H plus to donate, so H2O liquid. And C6H6O6 2 minus. And now that most certainly is a base. I don't need to look that up because it is only a base. You'll see that on the right-hand side. Okay? That is guaranteed. However, okay, we need some calculations to do this basically with this here. So, a couple things here. Let me just do a quick calculation here. Just got to check something. Nope, not that. Okay. All right. So now, one thing to keep in mind here, after we do this here, so think about this, and this is kind of, well, I kind of told you about this a little bit yesterday here. Remember, if we get to this first one here, right? So we get to the first endpoint right here. At that point, it's all changing, right? It's all completely new stuff that we're talking about here. We are talking about this particular ion here reacting with the hydroxide. What's the concentration when I start that second titration part? Because I do the first titration, and I use these numbers here, right? 0.5 molar, 0.40 molar. But what's the concentration of HC6H6O6 minus? Think about that for a second. I'm going to do my second, like I said, my second titration here. So I do the first one. What, by the way, what's in the burette? What's in the burette part? Sodium hydroxide, yes? What's the concentration of that sodium hydroxide? 0.4 molar, right? Has that changed at all? No, that's still 0.4 molar, right? I'm still adding it. So this is still 0.4 molar here, yes? That hasn't changed, right? What's the concentration of this, though? What's the concentration of this? What's in the bottom part of that beaker? Well, it's this now, right? Yes? That and water. But listen, up here, look, 0.0125 moles reacted with 0.0125 moles to produce what? 0.0125 moles and 0.0125 moles, correct? So I'm starting with 0.0215 moles here, am I not? Correct? But wait a minute though. How much volume do I have in the bottom there now? Yeah, I don't have what I started with, right? Because I've added a bunch of stuff, right? At that equivalence point, we just found it takes 31.25 milliliters of sodium hydroxide. So it takes 31.25 milliliters of sodium hydroxide basically in 31.25 milliliters of water, yes? So 31.25 milliliters of water, really. And I started with 25 milliliters of the acid. So altogether, right, look right here. I had 25 milliliters. I added 31.25 milliliters. So really, down here, I have 25 and 31.25, which is 56.25. Is that right? Okay. So I actually have that sitting there, right? So from those two, I could calculate the initial concentration, which, by the way, works out to be, let's see, somewhere here, 0.22. Is that right? I think that's right. Yeah? N and V, what's N and V? C? What is it? Come on, guys. 0.0125 divided by 0.05625. Yeah, 0.22 repeating, yes? Molar. Okay? So that's really what I'm starting with here. Okay? That's really what I'm starting with here. 0.22 molar. And look, here's the thing though, and this is the part that kind of confuses people, and maybe I should even write out another equation though, right? Remember, how many moles do I have here? That's still the same, right? 0.0125 moles. So really, how much does it take to basically react with that? 0.0125, right? So 0.0125 here would react with those 0.1025 moles here. By the way, all I did here was just calculate the initial concentration that I'm starting with for that second titration. That's the initial concentration, right? That's all I did there. But 0.025 moles has to react with 0.0125 moles here. What's the volume down here? 0.03125. Right? It's another, do the division there, guys. 0.0125 divided by 0.40, it's 31.03125, right? So it takes another 31.25 milliliters, correct? So remember when I said, look, back up to here, all the way back up to here, guys. Remember when I said this was X, and this was 2X, right? Is that not true? Look, the first part took 31.25 right here. This takes 31.25, so the equivalence point there is what? 62.50 milliliters altogether. Okay? True? Yes? Yeah. Because that's why. Because you're using the same number of moles to start with as you finished with at the other one, right? You still got 0.0125 moles. You're using 0.0125 moles to react with another 0.0125 moles. The concentration didn't change, so it's going to take the exact same volume. Okay? For the second one. Has to. That's why it's always X and always 2X. Always. And if you did another one, it'd probably be 3X. Okay? Because it takes always the same amount of volume every time that you do this. That's 31.25. What we did, remember, when I calculated, you might say, well, yeah, but your answer was 31.25. I know, but we started here, and I went to here, so that was 31.25, right? That section was 31.25. For a total of, if I started from 0, 62.5, yes? Okay? So those are, like I said, those are some of the things that you need to know. Is this, by the way, what's this? Well, that's probably a pH greater than 7, yes? Because obviously when you're done this, look, C6H6O6 2- is a weak base. That's, you don't even need to look it up. It's only a weak base. Okay? So that's not amphiprotic anymore. That is a weak base. So I can tell you that for sure. Okay? If you wanted to estimate pHs and stuff like that, you probably still could. Okay? You know, for the first one, if you want, let's see here. Where's the first one? We said that was a base there. And if you had to look that up, let's see. If that's the base, we get HC6H6O-. That's, you know, there's 7. There's the base there. There's 14. So I would say probably, I don't know, 8, 9, maybe somewhere in there. So I'd expect this to be approximately 8 to 9, somewhere there maybe. And then if you look up H, the other one here, the C6H6O6 2-, if you look that one up, that's pretty darn close to the bottom here. Now, is it going to be 12, 13, 14? Well, probably not. That's a hydroxide kind of thing. It could be, but I'd say here probably approximately 10 to 11, somewhere in there maybe, roughly. And then you could pick some indicators based on that. Okay, maybe 12, I don't know. It's really hard to say. You got some extra work to do there. Basically what you need to do for that, if you really want to figure that out, I kind of skipped over that part yesterday. So if you really want to know what to figure out that pH is, you could. I'll show you if you really, really want to know. But, I don't know. We might have enough problem with this, perhaps. I don't know. That might be enough work for you for the day. If you want to find out the other stuff, I'll show you how to do the other ones from yesterday, and then you can apply them to this, which are the same. Okay, but there is a lot more work there. Yep. Yeah. Okay, good. Questions, anyone? Okay. Start with the graphs. Okay, you're not trying to make a pretty graph here. You can see mine's probably not proportionate. I have no idea what the pHs are going to be when they start with. Doesn't matter. Okay, you want to start with a graph. Yes, you can calculate this. You know, this here turned out to be higher than 7, so should my graph be shifted up? Probably. I don't care. Whatever. Okay? As long as you know what those equations are and basically how to calculate that stuff. All right? So keep that in mind. All right? One last thing. Do you have to, okay, we did the first one here. I calculated the equivalence point, 31.25 milliliters. I marked it on the graph. I went to do the second one, and I found out it was 31.25, and I doubled it, and I get 62.5. Do you really need to do this calculation down here? And the answer is probably not. Okay? Are you going to have to do that in diploma? Probably not. Are you going to have to do that in test? Probably not. You do need to know, though, absolutely, that If the equivalence point is 31.25 for the first endpoint, then it's 62.5 for the second one. Absolutely do need to know that. Yes, always. So you need to remember that, but otherwise, do you have to calculate that? You could, okay, but you probably don't need to. All right?